Hello everyone. Today we're going to look at the slope deflection method. We're going to learn how to derive the slope deflection method. Now, before we delve into this, we should know some few things. Okay, to this topic, slope deflection method. Now, by now we should know that this method is part of the methods used to solve indeterminate structures, for instance, indeterminate frames, indeterminate beams. And recall, when I mean indeterminate, externally, of course. When I mean indeterminate externally, talking about those beams, those frames that cannot be, that we can't get their reactions by using the equilibrium equation. So we have to resort to something else to get their reactions. So now, slope deflection method was introduced by George A. Maney. Sorry about that. George A. Maney. Of course, you use the you see some of the applications of the Morse theorem, so we can also give more credits here. So one of the benefits of learning, first of all, this solving indeterminate structures, we can solve them using the force methods. We can solve it using the displacement method. And sorry, I need us to I'm also learning, so these are the two I know for now. So for these displacement methods, we have the moment distribution method, and we have the slope and deflection method, the one we'll be doing today. So as regarding this slope deflection method, it's a wonderful method because comparing to the force methods, we can use it to solve structures, beams, for instance, that has a high number of spans. We can use it to solve it easily. Not that we can't use force method to solve it, but we have to go through a lot of work. But it can be expedited using slope and deflection method, basically, or sorry, the slope deflection method. So learning this is a plus for you because it is also a prerequisite to the computation of the modern matrix method. Modern matrix method is what we'll be doing later on. We'll be doing that later on. So, I mean, when you're learning this, you're like basically killing two birds with a single stone, right? You're learning it to like solve and applying the knowledge to like solve beams, frames, and everything, indeterminate structures, right? Now, and you're also learning it for the future because you're going to be needing the knowledge as a foundation to step into the modern matrix method to understand it more. So it's a plus. So please learn it. So before we start this derivation, we should understand that this method, slope deflection, just takes into account the bending deformation of the beam. Just the bending deformation. Here we'll be dealing with member end moments a lot. You should know also that anytime there are always member end moments before we start. You should know this, that there are always member end moments. Very, very important. There are always member end moments. So I've talked about bending deformations now. I've said that we're going to be using just the bending deformations. No, we're not considering the shear deformations. So what are we using the bending deformations for? We are basically comparing or trying to find a relation with the bending deformation, that is the member end moment. We are getting a relation that has the member end moment and has the degree of freedoms. That is, imagine an equation where you'll be saying a member end moment and you also be saying degree of freedoms. But what do I mean by degree of freedoms now? Degree of freedoms. Let's say you have this beam. Of course, it's indeterminate. And here is A, here is B, here is C. Of course, the slope here at this point is 0. The translation also is 0. I mean, it's just moments we're having. For here, is also moments we're having for C. For A also, which I just discussed, is also moments we're having, something like this. Of course, we assume a direction. Now, for B, translation is 0, but slope will occur here. There will be a rotation here at B. Now, when I'm talking about degree of freedoms, I'm looking at displacement. And when I talk of displacement, I'm talking of two things: translation and I'm talking of rotation. So in essence, when I say how many degree of freedoms do I have in this beam, once again, let's look at this beam. So that is how many, okay, let me put it in a more explicit way. How many of these degree of freedoms are unknown? Okay, let's look at it. Here, the slope is known. Displacement is known. Here, displacement is known, but the slope is unknown. Here also is the same thing as what happened in A. So in essence, we can say that this above structure has just 1 degree of freedom. Because it has 1 unknown rotation at B. Because it has 1 unknown rotation at B. That is just it. And now, when we say something has degree of freedom, we can say that it is kinematically indeterminate. For instance, if the structure has 2 degree of freedoms, that is, we have 2 maybe rotations, for instance, then we can say that the structure is kinematically indeterminate. Indeterminate. to that degree of freedom, which is maybe if it has two degree of freedoms. So that's just it. Now let's get into business. So let's imagine we have a continuous beam of this kind, and we have an arbitrary loading. Now we're putting this beam into like the worst case scenario, that is, we'll be accounting for support settlement also. We'll not just be accounting for influences like loads. We'll also be accounting for the support settlements. So let's say it's supported hinged, and yes, this is A, and let's say at B it's synced. It's settled. I said synced. Oh jeez. Yeah, so settled also, yeah, the support and settled. Now, if we go back to our elastic curve tutorial, we can, oh no, I haven't published it yet, but I will do that soon. But you know that the elastic curve for this would be something like this. Something like this. Raise this here. Yes. So, elastic curve. Elastic curve. We see theta C. Now, there's also something called a chord. A chord is basically, let me use a very thin line. A chord is basically that line, joining the ends of the elastic curve. So I mean, if I join this end to this end, if I join this end to this end using a straight line, then I have my chord, right? Exactly. I have my chord. Now, we have something called the chord rotation. Sorry about this. We have something called the chord rotation. The chord rotation is also with respect to the undeformed axis, the axis with the red. Give it a symbol of phi. So, similarly for this, our chord rotation, phi is the same, it's the same phi. So, get the gist. Now, let's go back to Morse theorem. Let me zoom this a little. A minute, guys. Oh my. Okay. Yes. a minute. Morse theorem. Now, remember that in Morse theorem, guy found a way to like use the elastic curve to form relationship between the tangential deviations to the the tangents. I mean, use the elastic curve to form relation between the rotations, just several things like that. So let's do the same thing here. So using Morse theorem, and please note remember that this is another undeformed axis, the one on red. We have two undeformed axes. We have this and we have this. So remember that this, let me extend it, is part of it. Let's give this a distance of let's give it that symbol. Now, let's now use a Morse theorem. In Morse theorem, to establish, the distance from here to here, I mean, this is our elastic curve, this lemon line all the way. So from here to here, we can give it a distance of this notation, I mean BC. Why did I do BC? That's the next question. Why did I do BC? I did BC because at B, it started from B here. It started from the point on an elastic curve all the way down to the line drawn from this particular point on the elastic curve. This tangent line drawn, touching this axis, this vertical axis. So from here to here. So I have delta BC, tangential deviation. Similarly, for this, I have delta and still going to extend. This is still going to extend. Well, let's see, let me draw it again. Let's say it's all the way here, for instance. So it means that let me just draw a reference axis, So another reference axis. Using the same principle I just did for this guy, to establish it in this right region, I can say that from this point on an elastic curve at C, this point here, on this elastic curve, all the way up, I can call it delta CB, because it's starting at C and it's going to the one at B, the tangent line at B. Do you get? Starting at a point and going to a line. Starting at a point on the elastic curve and going to a line, the tangent line, on that same vertical axis. So it means that the overall distance here would be delta plus delta CB, this. Similarly, the overall distance here would be this plus Now, having established this, we can now, there's something we need to know. There's a law called the law of superposition in structural analysis. Law of superposition. That law is basically saying that maybe I have a lot of forces acting on this structure, a lot of forces, and it will produce a significant, no, not a significant, maybe it produces an insignificant deformation. Of course, this scale is exaggerated. Maybe it produces an insignificant, deformation. To get that insignificant deformation, what I can do is that I can take one of these forces, apply it on that same location to the beam, plus take the next force, apply it on that particular force, plus take the next force, which is in this side, apply it on that particular beam at that point. The total effect that I have from each of these, for instance, from A, B, C, must give me what I have in D, the total effect. So what I'm saying is that, in essence, the principle of superposition is saying that when you have simultaneous loading applied on a structure, maybe a external loading applied on the structure simultaneously, of course it's going to produce an effect. But now the principle of superposition is telling us that that effect can be gotten by just simply adding the effect caused by each of those forces acting separately. But this law would hold if the structure you're dealing with is elastic. It follows Hooke's law, and it will also work if it doesn't deform excessively, if it doesn't deform significantly. Now you may be wondering, how do I know? Well, the truth is that most of the structures we see are actually, we can use this principle of superposition for it because it follows Hooke's law. How do I know it follows Hooke's law? How do I know that the deformation is not so excessive? How do I know that it follows this law of superposition? That is, we can use this law of superposition. How do I know? Well, I know because when we design structures, when we apply the service load, we ensure that deflection is not significant. So I can tell you that you can use this law of superposition for most of the structures that meets this criteria, that under service load, deflection isn't so significant. So we can move to something, okay, see the same thing, but I want to establish. Now, we said principle of superposition for a reason. We said it because we are going to be decomposing this structure. I didn't fully draw it well. Okay, I drew it well, yeah. We're going to be decomposing this structure separately. That is, we'll have the structure, the beam. We'll have the beam when it is just moment A acting. We'll have the beam when it is just, sorry, I said moment A, I mean moment B acting. We'll have the beam when it is just moment C acting. Then we'll have the beam when it is the external load acting. And we're going to apply the principle of superposition to it. We'll add the effects and everything. So, the first one, due to member C, due to MCB, the first moment. Remember, I said, let me take you back. Remember, I said we're decomposing. This is the first guy. So due to MCB or MBC, anyone basically. MBC, and just as long as you are still going to add them at the end of the day, you get me. So due to MBC to MBC. So if that is not quite clear, what I'm saying in essence is that when I had this structure that is on this load, I also add some effects. I think the direction was counterclockwise. So yeah, it was counterclockwise because I said we want to use a positive moment at those ends. So basically, I can say that this is equals to this. Plus this. Plus this. So that is just what I mean. That is what I mean. So due to MBC now, a minute please. Can fast forward it. So due to MBC, now let's give this L. Now, in order to, one of the reasons why we're doing superposition, remember I said effect, I was saying that, okay, the effect on one structure, the deformation on the structure that has all the loading acting on it must be equals to the deformation when you had each of the loading effects cause. So what is this effect I'm talking about? Of course, the displacement. This thing that we have been saying, for instance, the tangential deviations. Do you get? So, yeah, rotation is part also. So now, I have, of course, B once again, and C also. In order to get those displacements, those rotations, I need my elastic curve diagram so that I can use Morse theorem. Do you get? I need my elastic curve diagram so I can use Morse theorem. Once again, I'm adding, I don't know why this, I just feel like I should go back to it. Why am I adding this structure once again, these structures? Why am I adding it? Because I'm adding it because I know that any deformation, for instance, the total deformation I have, maybe here, maybe delta plus delta CB. When I had the deformation I get here, and the deformation I get here, and the deformation I get here, for these three members, it must give me delta plus delta CB at C. Similarly, the same thing for B. That is the reason why I'm breaking down the structure. That is, I'm decomposing by later on superposing. So, once again, I'm decomposing so that I can get my displacement, so that at the end of the day I can add it by superposing. But before I can get my displacement, I need my elastic curve diagram. But now, before you can get your elastic curve diagram, you need your bending moment diagram. Although, more specifically, your bending moment over your flexural rigidity diagram. More on that on our qualitative deflected shape, which is also known as elastic curve video. So let's draw a line for vertical consistency, and please bear in mind that this is B. I'm sorry for the background noise. Bear in mind that this is B and this is C. So of course we don't need to get the values for the bending moments of our rigidity diagram. We just need to get the shape. No, we just need to get the what's the name? Yeah, the shape. So of course the bending moment for this will be this way. Why? Because I mean this is concave down. This moment here, we'll bring it based on the bending moment convention. Of course, we'll bring it down. So when I know my bending moment, I can get my elastic curve for my bending moment over EI. So remember, bending moment over EI. So let's see. Now, if this is bending moment over EI, it means that once again, please, I'm doing the one due to MBC now. The moment here I'm dealing with is MBC, a moment MBC. I'm dealing with, you know, I said this structure can be decomposed into this first moment separately, plus this second moment separately, plus this third external force. But for now, I'm dealing with the first moment acting separately and alone. So if it is acting alone, it means that this is how the bending moments diagram will be. So continuing, then I have draw my elastic curve. Now you should know that to draw an elastic curve, I'm giving you, but you'll know more when you get to the video. When you have a negative bending moment diagram, your elastic curve must have an hugging face, like, yeah, I said hugging, but it must have a frowning face. Yes. Let me draw it more underneath. Okay. So once again B, once again C. So this is just the purpose of drawing so here will be delta CB, I mean point C to tangent B. Similarly, here it will be delta BC. So you have started to see that I've started to obtain, if we can go to the future, it means that my delta this side has started to give me, you know, if I equate it to something, I've gotten one of them. That is, for that side I'll be having equals to delta CB. I'll see how the others, but I'll show you delta CB. But we'll still do that. We'll still do that later. Something relating to that, although. So now for most theorem, once again, whenever we are dealing with tangential deviation, we are dealing with moments of area under the what's the name? For instance, when we are dealing with if this is B, of course, and this is C. If we are dealing with MBC, it means that we are dealing with the moment of area under this M over EI diagram. I mean M over EI diagram, you get, that is MBC over EI, MBC over EI. That will be there. So once again, when I'm talking about delta BC, it means that I'll be getting the moment of area about B. That is, when I'm getting the centroid, I'll be coming from B. Similarly, if it is MCB, or sorry, delta CB, it means that I'll be coming from C when getting my centroid. Do you get? Or the moment of area. That is the area times the centroid. So for delta BC, I'll be having my moment of area as 1 over 2 MBC over EI times L over 3. Because it is about B, so the centroid will be somewhere here. You get? Somewhere here. So this will give me MBC L square over 6EI. Similarly, for delta CB, I'll be having, once again, the area MBC over EI L, fingers touching the screen, times the centroid, so L over 3, which will be equal, all these guys will be equal to MBC L square over 3EI. So in essence, for this, I have that delta BC will be equals to MBC L square over 6EI, and delta CB will be equals to MBC L square over 3EI. Keep this in mind. Now, we are not done. We have to now do the one when it is now that MCB is acting alone due to MBC. Oh, sorry, MCB. I've done MBC. Now it's MCB. That is the moment at end C, where the far end is B. Once again, we need the elastic curve, but we can't get the elastic curve without getting the bending moment diagram. Bending moment over flexural rigidity diagram. I'm sorry. I'm fond of it. So MCB over EI then elastic curve diagram, which is what we need. Now for this is a positive moment diagram. It means that we'll be having a smiling face as our elastic curve, and having a smiling face. So we need delta, mistake. We need delta. This guy. This guy. So So here will be obviously BC. I mean, here will be delta C at C to B. And here will be delta BC. You get, of course, slope at B, slope at C. Now, looking at this again, delta BC, which is basically the moment of area about B for the M over AI diagram, would be half. Looking at the bending moment diagram, to be half times MCB over EI times L times centroid. So delta BC B MCB L square over 3EI. Similarly, for this guy, we have delta CB to be half, I mean a triangle, MCB. Oh wow, I didn't even explain why it's like this, why it's half MCB. It is this L over 3. Well, this is L, of course. Of course, it is L. So it's like this because this is a triangle, so the area of a triangle, when I say the moment of area, I mean the area times the centroid. So area of triangle is half base. This is the base, which is L, and the height is MCB over EI. So I'm now multiplying by the centroid moving from C. This is the centroid expression if we are moving from C. And this is the centroid expression. This here, I'm sorry. This is the centroid expression if we are moving from B. Get. So, once again, I can see that delta CB is equals to, and see that I'm filling it small, L square over 6EI, then delta CB, okay, looking for, oh man, mistake, forgive me, half times, this is 6, 1/2 times I'm moving, okay, sorry, did it, okay, this is 6, so I'm on track, L square over, okay, 1, 6EI. L, this is L, MCB, L square over 6EI. So that's delta CB and delta BC, MCBL over 3EI. Simple. Now the last one, not the last one exactly, but the second to the last one, which is due to the external loads acting. due to the external load acting on it. Now, of course, this is span, and it's span moment. So, like this will be the bending moment diagram, positive. And elastic curve, if it's positive, it will be a smiling face. So I can say that at B, once again, C, L. So extend the tangent from B, extend the tangent from C, then say that this is rotation at B, rotation at C. Then from this distance at B to touching C on that vertical axis, red. Similarly, from C going down to B vertically, I say that this is CB, and I say that this is BC once again. Now, for this delta CB, I wouldn't want to we're deriving a formula. So if I just give you the area for this, what if in the external load, this particular external load, maybe if it's a UDL for instance, what if it didn't come out that way? What if it came out in another form? What if it came out in a normal point load, this external load? What do? That is the reason why for this particular due to external loads, when we decompose for the external load part, we don't find the moment of area under the for the bending moment over EI diagram. We don't find the moment of area because the loading can be any form. The loading can be any form, but we found the moment because the moment is always the same. I mean, moment is moment. Moment is moment. Moment is always the same, like the same moment now. I mean, moment. That's how it is. But if it is loading, the loading can change. And if the loading changes, the bending moment will change. The bending moment diagram will change. And if we just solve for this bending moment diagram, it means that we're just deriving specifically for this situation. But we're deriving a general equation. So guess what? We're not finding the moment of areas for this parabolic shape or cubic reasoning. But instead of finding the moment of area, we'll give it an expression. We call the expression GC over EI. I mean, it's a bending moment over EI diagram now. Now, what is GC? GC is basically the moment of area about C. Doing it this way, it makes it general because the loading can be of any form. And if I just put GC, when I've defined it that GC is the moment of area about C, it means that if at all you have any load, all you just have to do is find the moment of area about C to get GC. Similarly for this BC, GB over EI, all you have to do is for GB, to get GB, find the moment of area of any of the bending moment shape. If it's like this, maybe you have anyone, find the moment of area about B divided by EI. EI came from the fact that this is not just a bending moment diagram, but it's a bending moment over EI diagram. So that is one part of it. So now that we've done all this, going back to if you can rewind back, we have to keep note of all the things we've derived due to MBC. Okay, let's start with due to MBC. let's start with the right hand side. We pick this first. We're dealing with the deflection in this side now. So for this guy, we have noticed that the deflection is this. That is MBC L square over 3EI Yes, exactly. You have noticed that. But let's pause on this. Let's pause on this. Now, let's go back to the original, the diagram where it was not decomposed. Everything was together. We noticed that. Let's go back to it. I'm sorry for deviating. You notice that I can form shapes. What do I mean that I can form shapes? See this. Can you see a pink like the first shape I can form? The first shape I can form. Can you see? I can form this shape. Where this will be this and delta BC. Similarly, I can form another shape. Let me give it another color. Let me give it cream. I can form another shape. This dark green guy. So there you go. Please, please, I beg you guys, please forgive me the way it's rough. But when you are making notes, of course, it can be orderly, so you won't confuse. You'll be confused maybe later when you go back to it. So here was delta CB, and here was just delta. So let's put this two in mind. Let's bring it down. So we had this. We had this two. Delta CB, delta. And we had this delta C. Delta BC. So knowing this, it means that we can use our principles of simple geometry now. Exactly, simple geometry. So if we say that normally this is supposed to be tan, it would be okay. Yeah, this will be L. And yeah, opposite. So opposite over adjacent. You get similarly tan theta C. The same thing now. So, but remember, one of the reasons why we use principle of superposition was the fact that our deformations must be insignificant. That is, our rotation must be small also. Remember, I said the displacement and the deformations when I talk of the deformation. That is, when I talk of the effects when I'm dealing with the principle of superposition. The effect I'm talking about is translation. Another effect I'm talking about is rotation. So it must be insignificant. It must be just small. And if that is the case, it means that it cannot be tan theta. Check it on your calculator. Just press a very small number. You see that tan of that small number will give you that small number. So I will have this. Mistake. Same value. Exactly. Another thing that you take note, so take note of this information also. Another thing you take note of is the chord rotation, which is another shape you see. Let's use blue for the chord rotation. Yes, so another shape you notice here is for the chord rotation. Two actually, but I'll just use one is enough for what I'm talking about. Now I'm drawing a blue line. So this is another shape. So chord rotation L. So let me zoom on it here. I'll be having something like this. A triangle, the chord rotation, and this. So taking this down now. Sorry, I have to keep all these details. That's why I'm not clearing it. And I'm sorry. So we can say that it's the same thing. It would have been tan of the chord rotation, but the same insignificant stuff holds also. So this guy. So it means that I have three foundational equations now. These are the foundational equations. I won't lie to you. But let's build on it. Let's build on it. So from this guy, I can say delta CB plus delta is equals to this guy. From this guy, I can say delta BC plus delta is equals to delta CL. A mistake. Delta. Did I say delta? Sorry, rotation CL. Rotation CL. Rotation CL. What am I doing? Okay, yes, that is it. So this guy, substitute this guy into this place also. Then I have delta CB plus, and is equals to also. Well, doing all the mathematics, or let me just show it. Let's see. Equals to delta CL. This supposed to be delta B, rotation at B. You get. So doing all this, I'll be having CB equals to delta subscript B minus this. Then having these babies. So once again, we have decomposed the structure for a reason. That is, what do I mean? We decompose the structure for a reason. Once again, I will keep on explaining. It has to sink. I'm sorry. So this was the external beam. So at C, and I said that is a counterclockwise movement. At C, let's say we want to find the, or how would I explain this now? Okay, I think the best way to explain this is this way. Delta BC of this main structure must be equal to delta BC of the others. Do you understand? That is the displacement from here to here of this structure. Delta BC of this main, combined loading must be equal to, okay, let me write it down. Delta BC of the main must be equal to delta BC due to MBC plus, that is acting separately now, they're acting separately, which we derived at that time, due to MCB plus delta BC due to external loads. The main. So I can now say that delta BC main is equal to, let's go and find it, delta BC MBC. That is for the first one, delta BC MBC. That's MBC L square over 6EI. MBC L square over 6EI. Plus, if you look at the others, you'll see that it is this. L square over 3EI plus GB over EI. Now, there's a modification that has to go on in this equation that we just derived. Remember that for the main structure, we're always going to be comparing the main one, that is when it is acting. In principle of superposition, when you apply it, you have to just keep on comparing the main one when everything was acting together and the ones when they were acting separately. Now, delta BC in the main one was below, okay, sorry, this is not the main one. Okay, this is the main one. Now, delta BC of the main one was below the deformed axis. See this gold I'm doing now? Was below it. It was below the undeformed axis. Of course, the undeformed axis. It was below the undeformed axis. So, we must ensure that the other delta BC, the babies, must also be below the undeformed axis. Let's find out. For this, delta BC is above. So we're going to put a minus to convert it to below the undeformed axis. I mean, this is the undeformed axis. So this one is above it. But delta BC in the original one, the parent, must be consistent in direction also. So we must give this a negative in that equation. We must adjust it to conform to this likeness. The child must be the same as the father. But now, delta BC here, okay, it conforms, good. It's also underneath, so positive. Similarly, delta BC is also underneath. So the only thing that we're going to be changing is this negative guy here, putting the negative to MBC L square over 6CI. So putting the negative here, that's the only thing we're going to be adjusting in this equation. That is, we'll now be having, writing it like a mathematical person, we'll be having delta BC is equals to MCB L square over 3EI plus GB over EI minus MBC L square over 6EI. So, likewise, doing and repeating the same step for delta CB, I'll be having repeating the same thing, adjusting delta CB and everything. I'll be having I think here delta CB was up, so I must try to make sure that everything is up. Initially, I'll be having, when adding the babies of CB, I'll be having everything positive. Six AI minus GC. Now, delta CB is up. I must try to make sure that everything too is up. So the only one that is not up, the two that are not up, is the one due to the external load. Can you see it's down? For delta CB is down. This one too is down. So these two are not up. So I'll be giving it a negative. But this one is up. This one is up. This guy here. This delta CB guy here is up. Why am I saying? Why am I even saying up? Why am I favoring up now? I'm favoring up now because delta CB is above the undeformed axis. Can you see? It's above, so I'm favoring up. That is, my babies must also be up. So this one is up, fine. A positive answer for this. As is positive, so it will only be the positive one. The others will be negative. I give it, it's supposed to be positive before positive. But now that I know that I have, seen some things, then I'll give it a negative here. And I'll give it a negative here. But recall that delta CB is equals to this. Also the same thing. So all these delta CB I've done, I will now put it inside those foundational equations that I just get. So minutes. All right. So putting everything. Then solving and solving, simplifying, I'll be having from this guy, I'll be having MBC over 3EI minus MCB L over 6EI minus GC over EI L. Again, the same thing for the other guy. I'll be having now you can breathe. But there's something that you should do. Something that you should do. You're having two M's now, which is not bad. But to make life simpler, let's find it for one M. The only way to do this is to solve simultaneously. That is, I'm going to, okay, let's say this equation 1, for instance. Let's call this equation 2, because I'll be calling them out. So now I'll have to put MBC inside this guy here. Okay. But to do that, I have to multiply by half. Why am I multiplying by half? So that I can be having MBC over 6CI. So I'll just substitute it directly. You get. So multiplying equation 1 by half. Equation 1 by half. I'll be having MBCL over 6EI equals to plus that's with EI plus GC over 2EIL. Then I can now substitute this guy inside this equation. Can you see the reason that I multiply by half so that it can just be MBCL over 6EI? I'll just substitute directly. Upon substituting, it's a long step, it's a long process, kind of long, so you can just solve then. But what you have is this. You'll be having MCB, you're substituting inside this equation, inside equation 2. So if you are substituting for MBC inside equation 2, it means that it will just be MCB that will be left. So we can make MCB the subject of formula. Then you have 2EI over L open brackets 2 theta C plus B minus 3 over quad rotation plus 2 over L square GC is the moment of area about C due to external load and that of B. Now, that's for MCB. When you repeat the same step when you say that, okay, instead of substituting MBC over 6CI now, let me substitute MCBL over 3I. When I substitute it inside here, it means that I'll be left with MBC. So I can now make MBC the subject of formula, and I will have MBC is equals to 2EI over L 2 theta B plus theta C minus 3 times quad rotation plus 2 over L square 2 GC minus GB. Now, there's something called the fixed end moment. So anytime, of course, when we're talking about fixed end, in a fixed end, for instance, the slope is 0, displacement is 0. So if to convert MCB to a fixed end moment, that is the moment at C, for instance, maybe the moment where the near end is at C and the far end is at B, which is MCB, to convert it to a fixed end moment, that is this expression here, I can convert it to a fixed end moment by setting all my slopes to 0. Let's say, for instance, and yes, the only way fixed end moments can work, the only way you can convert it rather to a fixed end moment is if you have it both fixed at both ends. That is B and C. So it means that theta B will be 0, theta C will be 0. Likewise, delta will be 0, 0. So we can convert MCB to a fixed moment by setting all those to 0. Upon setting everything to 0, I can now say that MCB is equals to 2 over L square GC minus 2GB. Similarly, FEMBC equals to convert into a fixed moment, 2GC minus GB. Now, if these are my fixed moments, if these are my fixed moments, and this guy are my two equations, it means that I can convert these two equations to something better. That is MCB for the first one is equals to 2EI over L 2 theta C plus theta B minus 3 this plus FEMCB. MBC similarly the chord rotation plus FEMBC. Ladies and gentlemen, here is the slope deflection equation. Thank you for your time. We'll talk about some other aspects when we are solving.